Welcome to The Explainer. Today, we're diving into a massive Unit 1 mega review, Mastering Complex Numbers. We're going to cover basic operations with solutions for Exercise 1.6, blast through Review Exercise 1, and wrap the whole thing up with a Class 9 Mathematics summary for Unit 1. Let's get right to it. First up, a quick reality check. Did math literally just get unreal? You know, for years we're told you absolutely cannot take the square root of a negative number. But what if I told you that squaring a number could actually equal -1? Welcome to the wild world of the imaginary. Level 1, Mastering Complex Operations. Let's just jump in and break down how to actually do basic math with these imaginary numbers. So what exactly is a complex number? Think of it like a mathematical combo meal. You've got the formula, z equals a plus ib. It pairs a standard, everyday real part, that's your a right there, with an imaginary part, the b, which is hitched to that letter I. And I, well, that's just a stand-in for the square root of -1. Okay, so how do we actually handle them? When it comes to adding and subtracting, it's all about matching like terms. Honestly, it's just a sorting game. You group the real numbers with the real numbers and the imaginary ones with the imaginary ones. You never, ever mix the two. Let's actually look at this addition rule in action. Say we want to add the complex numbers 6, 9, and -1, 2. All we do is combine the first numbers, so 6 plus -1 gives us 5. Then we just combine the second numbers. 9 plus 2 gives us 11. Boom, our brand new complex number is simply 511. Super easy, right? Now multiplication, that gets a bit spicier. You're going to expand it out exactly like you would with standard binomials in algebra. But here's the real trick, the absolute crucial thing to remember. Whenever you multiply I by I, you get I squared, and that I squared instantly flips to a -1. It literally changes the entire DNA of your equation. And as you'll see here, this brilliantly illustrates exactly where our formulas come from. Division, I know, looks like an absolute beast of a formula. No way around it. But seriously, don't let it intimidate you. It's actually just derived from one clever little trick. You multiply the top and bottom of your fraction by the denominator's conjugate, and that completely knocks out the imaginary number from the bottom. Moving right along to level 2, cracking exercise 1.6. Now that we've got the tools, let's put them to work. So, exercise 1.6 is basically packed with these complex operations just begging to be simplified. We're talking addition, subtraction, and yeah, some pretty gnarly looking fractions. But let's zero in on one of the absolute toughest problems in the bunch. Let's see how this plays out when we tackle a really tough division problem. Question 1, part 9. We've got 3, -7, divided by 3, 2. First things first, identify the parts. A is 3, B is -7, C is 3, and D is 2. Now plug those guys straight into that massive division formula we were just looking at. Step by step, we multiply the top, square the bottom, and simplify it down. So we end up with 9 minus 14 over 9 plus 4, and eventually it perfectly simplifies down to our final result, -5 over 13 and -27 over 13. Flawless victory, guys. All right, level 3, review exercise 1 breakdown. Level cleared. Now let's blast through a rapid-fire review. We're looking at these fill-in-the-blank and true-false questions. They're basically designed to rigorously test if you actually understand the core concepts. So I want you actively thinking about the answers right along with me. Okay, quick question for you to chew on. What is the multiplicative inverse of the square root of 5? Just think for a second about what you have to multiply a number by to get exactly 1. Boom! It is exactly 1 over the square root of 5. And why is that? Because multiplying the square root of 5 by its reciprocal perfectly cancels out the numerator and the denominator, leaving you with a solid, clean 1. Next up on the review, let's play a little true or false. Does multiplying two complex numbers, like a, b, and c, d, just mean multiplying their parts straight across to get ac, bd? What do you think? Absolutely false. Please don't fall for that trap. Think back to our spicy multiplication rule from just a few minutes ago. The real formula is way more complex. Because that I squared turns into a -1, the actual product requires cross-multiplying and subtracting, which gives us AC minus BD, AD plus BC. And here we are, Level 4, Unit 1 Mega Summary. We are absolutely blazing through this material. Time to face the final boss. This ultimate summary page beautifully condenses all the laws and properties of real and complex numbers we've conquered in this entire unit. Seriously, if you're going to screenshot one thing from this explainer to study later, this is the goldmine right here. Let's rapidly compare those essential properties of real numbers for both addition and multiplication. You've got the closure property, meaning adding or multiplying real numbers always spits out another real number. The commutative property, which proves the order doesn't matter at all. A plus B is exactly the same as B plus A. And the associative property, showing that how you group the numbers doesn't change your final outcome one bit. And guys, we absolutely cannot forget the laws of exponents. These rules brilliantly dictate how powers combine, multiply, and distribute across your equations. When multiplying the same base, you just add the exponents. When taking a power to a power, you multiply them. These are basically your math cheat codes for simplifying crazy expressions in just seconds. Finally, let's look at this comparison. It perfectly illustrates the overarching difference between standard radicals and complex numbers. With a radical, you're just looking for a standard root. But with a complex number, we're purposefully pulling a negative out of a square root, essentially inventing I, to create a hybrid number format. It lets us solve equations that standard math simply can't touch. You've mastered the operations, aced the exercises, and conquered the Unit 1 summary. But before we wrap up this explainer, I really want to leave you with this final thought. If I is entirely imaginary, literally just a concept we made up to solve tricky equations, how do modern engineers use these exact formulas right now to design the real-world electrical grids powering your home or the quantum computers shaping our future? It turns out you actually need imaginary numbers to build a very real world. Keep questioning, keep learning, and I'll catch you in the next explainer.